And that then gives us these things called algorithms. And when it comes time to code, which we're about to do too, code is just an implementation in a language the computer understands of an algorithm. Now, this assumes that we've come up with some digital way, that is to say 0 and 1 based way, to represent names and numbers. But honestly, we already did that. We came up with ASCII and then Unicode to represent the names. Representing numbers is even easier than that. That's really where we started. So code is just about taking as input some standardized representation of names and numbers and spitting out answers. And that's truly what iOS and Android are doing. When you start doing autocomplete, they could be searching from the top to the bottom, which is fine if you've only got a few friends and family in the phone. But if you've got 1,000, or if you've got 10,000, or if it's not a phone book anymore, it's some database with lots and lots of data, well, it stands to reason that it'd be nice maybe if the computer kept it all alphabetized, just like that book, and jumped to the middle, then the middle of the middle, then the middle of the middle of the middle, and so forth. Why? Because the speed is going to be much, much faster, logarithmic in nature, and not linear, so to speak, in nature. But we'll revisit those topics as well. But for now, before we get into actual code, let's talk for a moment about pseudocode. So pseudocode is not one formal thing. Every human will come up with their own way of representing pseudocode. It's an English-like or human-like formulation of step-by-step instructions, just using terse, correct English, or whatever human language. So for instance, if I want to translate what I did somewhat intuitively with that phone book by just dividing in half into step-by-step instructions I could hand you, or nowadays like a robot or something like that, well, step 1 was essentially to pick up the phone book, which I did. Step 2 was I opened to the middle of the phone book in the third and final algorithm. Step 3 was look at the page, as I did. Step 4 got a little more interesting. Even though I didn't verbalize this, presumably I was asking myself a question. If the person I'm looking for, John Harvard, is on the page, then I would have called him right then. But if he weren't on the page, if he instead were earlier in the book, as did happen, well, then I'm going to go to the left, so to speak. But more methodically, I'm going to open to the middle of the left half of the book. Then I'm going to go back to line 3. That's interesting. We'll come back to that in a moment. But else, if the person is later in the book, well, I'm going to open to the middle of the right half of the book and then go back to line 3. Now, let's pause here. Why do I keep going back to line 3? This would seem to get me doing the same thing forever, endlessly, but not quite. Why? Yeah, so because I am dividing the problem in half, for instance, on line 6 or line 9, implicitly, just based on how I've written this, the problem's getting smaller and smaller and smaller. So it's fine if I keep doing the same logic again and again, because if the problem's getting smaller, eventually it's going to bottom out, and I'm going to have just one person on that page that I want to call, and so the algorithm's done. But there is a perverse corner case, if you will, and this is where it's ever more important to be precise when writing code and anticipate what could go wrong. I should probably ask one more question in this code, not just these 3. What might that question be? Yeah. Yeah, so if John Harvard is not in the book, there's this corner case where what if I'm just wasting my time entirely and I get to the end of the phone book and John Harvard's not there? What should the computer do? Well, as an aside, if you've ever been using your Mac or PC or phone and the thing just freezes, or like the stupid little beach ball starts spinning or something like that, and you're like, what is going on? Some human at Google or Microsoft or Apple or the like made a mistake. They forgot, for instance, that fourth uncommon but possible situation wherein if they don't tell the computer how to handle it, the computer is effectively going to freak out and do something undefined, like just hang or reboot or do something else. So we do want to add this, else quit altogether. So you have well-defined behavior. And truly think that the next time your computer or phone spontaneously reboots or dies or does something wrong, it's probably not your fault per se. It's some other human elsewhere did not write correct code. They didn't anticipate cases like these. But now let's use some terminology here. There's some salient ideas that we're going to see in Scratch and C and Python and these other languages I alluded to earlier. Everything I've just highlighted here, henceforth, we're going to think of as functions. Functions are verbs or actions that really get some small piece of work done for you. Functions are verbs or actions. Here, though, highlighted is the beginning of what we'll call conditionals. Conditional is like a fork in the road. Do I go this way? Do I go this way? Or some other way altogether? How do you decide what road to go down? We're going to call these questions you ask yourself Boolean expressions, named after a mathematician Boole. And a Boolean expression is just a question that has a yes or no answer, or a true or false answer, or a 1 or 0 answer. It's a binary state, yes or no, typically. Otherwise, we have this, go back to, which is what we're generally going to call a loop, which somehow induces cyclical behavior again and again. And those functions and those conditionals, Boolean expressions and loops and a few other concepts are pretty much what will underlie all of the code that we write, whether it is in Scratch, C, or something else altogether. But we need to get to that point. And in fact, let's go and infer what this program here does. At the end of the day, computers only understand zeros and ones, so I claim here is a program of zeros and ones. What does it do? Anyone want to guess? I mean, we could spend all day converting all of these zeros and ones to numbers, but they're not going to be numbers if it's code. What do you think? That's amazing. It does, in fact, print hello world. All right, so no one, except like maybe you and me and a few others in the room, should know, and that was probably a guess, admittedly, or advancing on the slide. But why is that? Well, it turns out that not only do computers standardize information, data, like numbers and letters and colors and other things, they also standardize instructions. And so if you've heard of companies like Intel or AMD or NVIDIA or others, among the things they do is they decide as a company what pattern of zeros and ones shall represent what functionality. And it's very low-level functionality. Those companies and others decide that some pattern of zeros and ones means add two numbers together, or subtract, or multiply. Another pattern might mean load information from the computer's hard drive into memory. Another might mean store it somewhere else. Another might mean print something out to the screen. So nested somewhere in here, and admittedly I have no idea which pattern offhand because it's not interesting enough to go figure it out at this level, says print. And somewhere in there, like this gentleman proposed, I bet we could find the representation of H, which was 72, and E, and L, and L, and O, and everything that composes hello world. Because as it turns out, in programming circles, the very first program that students typically write is that of hello world. Now, this one here is written in a much more intelligible way. Even if you're not a programmer, odds are if I asked you, what does this program do, you would have said, oh, hello world, even though there's a lot of clutter here. Like, no idea what this is until next week. Int main void, that looks cryptic. There's these weird curly braces, which we rarely use in the real world. But at least I understand a few words like hello and world. And this is kind of familiar, printf, but it's not print, but it's probably the same thing. So here, too, is an example of this hierarchy. Back in the day, in the earliest days of computers, humans were writing code by representing zeros and ones. If you've ever heard your parents talk about punch cards or the like, you're effectively representing patterns that tell the computer what to do or what to represent, like literally holes in paper. Well, pretty quickly early on, this got really tedious, only writing code at such a low level. So someone decided, you know what? I'm going to put in the effort. I'm going to figure out what patterns of zeros and ones I can put together so as to be able to convert something more user-friendly to those zeros and ones. And as a teaser for next week, that person invented the first compiler. A compiler is just a program that translates one language to another. And more modernly, this is a language called C, which we'll spend a few weeks on together because it's so fundamental to how the computer works. Even this is going to get tedious by like week 6 of the class. And this is going to get stupid. This is going to get annoying. This is going to get cryptic. We're just going to write print hello on the screen in order to use a different language called Python. Why? Because someone wrote in C a program that can convert Python, this is a white lie, to C, which can then be converted to zeros and ones, and so forth. So in computing, there's this principle of abstraction, where we start with the basics, and thank God we can all trust that someone else solved these really hard problems way long ago. Then they wrote programs to make it easier. We wrote programs to make it easier. You can now write code like I did with the chatbot to make things even easier. Why? Because OpenAI and other companies have abstracted away a lot of the lower level implementation details. And that's where I think this stuff gets really exciting. We can stand on the shoulders of others so long as we know how to use and assemble these kinds of building blocks. And speaking of building blocks, let's start here. Now, odds are some of you might have started here in like grade school playing with Scratch, and it's great for like after school programs.